Okay, now faster RCNN, okay, that's like one level higher. Now that wanted to kind of do away with this block itself. So the idea was that, right, can you actually generate a network that can actually output these region proposals. I mean, that's the ideal thing you would have liked to have, right? Have a network that can actually do that. How would you do that? That's the goal of faster RCNN. It wants to build a network that can actually throw up these boxes, that can tell likely regions of interest, which are your region proposals. How would they have done it? Huh? Have you heard of anchor boxes? If you have not, okay, then in that case, right, okay, what is your idea? Anyway, you tell. It is somewhat like that, okay, this is somewhat like that, but now right, in this case what we need really are these boxes, right? We need bounding boxes. Now, in order to get bounding boxes, right, what they do is, they actually imagine, see, for example, I have an input image. Okay, let's say that right, let's say that I have an image, and then I know that right, there is an object here, and I also know that there is a ground truth box there, right, and then there is another object here. I know that right, there is a ground truth box corresponding to that, and so on. But then during inference time, right, I mean, I cannot use this knowledge, because during inference time I don't know where the boxes are, right. Therefore, you have to have some way to kind of use this information to flag. Now, if you look at fast RCNN, right, it came from a proposal to the feature map. Right, feature map volume, that is how it came, right. It took the proposal and then found out where exactly is this guy. Now, faster RCNN does exactly the ulta, it goes the other way. Now, what it does is, it assumes that in the image you have at every pixel, this is again, this is a hyperparameter, at every pixel you have 9 anchor boxes, at every pixel. That means, right, it is trying to say that, imagine that you have anchor boxes all around. What are these anchor boxes? These are exactly your RPs, right. So, this is like a region proposal, and by anchor boxes what you mean is, rectangles of 3 shapes, square, and then whatever, right, elongated and kind of tall, and then the other 3 are like the scale. Okay, you can have like 1, 2, 4, right. So, you have kind of 9 anchor boxes. You can change this. It is a hyperparameter. So, what it it kind of, right, looks like this, right, if you actually right, imagine. So, it is like saying that at every pixel there are these 9 guys, right, waiting to flag something. Okay. Now, what happens is, when you have this feature volume, see, as far as faster RCNN is concerned, right, this part is exactly identical to fast RCNN. Okay. The only thing that really is new is here. Okay, and you see, as I said earlier, right, when what you want, I mean, if you had this one, a network to actually do that job of flagging this one proposals, let us call this RPN, right, RP network. So, let us call this a region, this one a proposal, this one a network, right, let us call this RPN, right. Now this network, its job is to actually do some kind of a, let us say that we also want it to be a classifier in this case, but then what kind of a classifier? It should be all that we need is, it should be a binary classifier. See, right, imagine the one below is going to do a lot more. See, the region proposal, that is what I said, right, the region proposal, the selective search, when it flagged, that you could have bounding boxes here, bounding boxes there, these RPs, right, proposals, when it threw up, it never said what it contained, right. It only said that this region could be potentially interesting. It does not have knowledge about what it contains. It is like saying that here is a likely region of interest. So, that is all you want from RPN. You want to say whether it is 1 or 0, is it background or probably, right, is it foreground? Is it some foreground object? We do not want to know which object and all, that we will figure out later, right, because we have the class label for that and all we will do through the lower network. But this RPN, this network, all that we wanted to do is do a binary classification and simply right, tell us a 1 or 0 for, let us say, each of these anchor boxes. But then right, the point is, we do not want to send all the anchor boxes in, right. Now, we want to be able to do it in a smart way. What is a smart way of actually doing it? So, like I said, right, you take this feature volume, and then the fact is, right, when I actually go back, right, so what they do is, okay, here is where they kind of do something like a sliding window. So, I told right in the start that sliding window is actually not really a great idea when you kind of do it in the image domain, but then doing it in the feature domain when it is of a smaller dimension Okay, it's still right. It's not so bad. But then that's what they do. So what they do is, you take a feature volume, and then now you take an say n cross n sort of a window, and then try to find out where it goes. Okay, from kind of where this region comes in the image. And then what you will do is, so in that image you have got, like I said, you got anchor boxes all over, right, which are kind of virtually sitting there, right. They are not really, I mean, they are kind of virtually sitting there. Now what you do is, once you map it back to that region, what you do is you find out the IOU of each of those anchor boxes with respect to a ground truth box, if it exists there, right. It may not be there, no. It doesn't mean that every feature volume, if you map it back, right, it doesn't mean that there will be a ground truth box. If there is a ground truth box there, right, then you will find that there is one anchor box, right, which is coming kind of close to that, right. That's like, okay, right, that's in a way telling that here is a region proposal. So you have to fix your IOU somewhere, right. You have to say that some IOU greater than something could be actually, could be a potentially interesting region. Do you kind of see the idea, right? So just kind of back project, right, in a sense, go back, look at the image, look at all the anchor boxes there. If you have a ground truth box in that region, which you know a priori, right, that information I have, right, like I said, this I have with me, right, training time. So what you are trying to say is, you are making a network learn. So the idea is that, right, if I, during a test time, if I just give it this image, it should sort of immediately figure out that from here and all, right, I should get these region proposals, because it's learned, it's trained for that, right. It just goes back, looks at that, and then does an IOE with respect to ground truth, finds out that there are a few boxes that could be actually potentially interesting, pass them on. Okay, but then what it will do is, so the idea is that, right, so the idea is like this, right, what it will do is, so here, right, so here it has a small network, right? It's a small network which does a training, in the sense that, right, out of these proposal boxes, right, it still tries to find out which one of them should be considered as a background, and which one of them should be considered as a foreground. The foreground doesn't mean it knows the object, simply means that it's a 1 or a 0. Okay, so which means that all, because you see, finally, okay, we realize that when you want to train this network, right, we also want to know which is the background and all, right, because you don't want to put boxes. See, the problem that will happen is, if you don't know the background, right, then one risk that you run is, you can, without, if you don't know the background, you can end up actually, right, putting a box there, because you don't even know how it looks. This used to happen with, if you look at these, look at the classical traditional approaches, this is always a problem. For example, right, in a whole image, you will have 5 faces. It will nicely put 5 boxes there, and then when you are just feeling happy, it will put one more box somewhere else, where you don't even see a face. There is no face there, but it thinks that there is a face there. That is because it does not know the background, and background is so rich. See, I mean, there isn't anything like a universal background, right? For every image, the background changes, whereas faces are universal. I mean, in the sense that, right, I mean, all humans look in a certain way, objects look in a certain way, but look at the background. Can you ever say that, in every image they can have a universal background? There is no such notion. Therefore, it is also important to know what is the background. That is why you have a small network here which does that job, right? Because it knows the labels, right? It knows where there is an object, where there is not an object. Therefore, it tells that these proposals, right? So all these, so you need a positive set of proposals, you need a negative set of proposals. All that comes from there. Positive, negative. That's all, right? Object or not. That's all, right? So, right, that part comes from there. It does a pruning also using some, say, NMS and all, and then after that, right, this comes here, and this network is exactly the same. Okay, because after this point, right, everything is the same, right. This guy will then go back, find the feature volume, squash it, and then, right, make them all uniform, learn end to end. Okay, that's the idea of faster RCNN. So the idea is that you actually have a network that will also flag those areas, right. So you want a region proposal network that can actually do it. And I thought that this idea, I don't think is that easy to get. I mean, the earlier one I would have thought is more probably, right, you just have to think a little bit and then you will get it, but this I thought is really smart, because it's not obvious, right. I mean, how do you get one network to flag proposals automatically, right. Okay.
You said that at each pixel there are 9 anchor boxes.
At each pixel, yeah, there are actually 9 anchor boxes, correct.
So I'm not able to get a proper sense of that. What is that exactly?
See, what this means, see, No, anchor box is like really a bounding box, right, if you want to think about it. So what you are saying is, at a pixel, right, you are imagining that one box is like this, you are imagining another box is like this, another box is like this, another which is of a bigger area. You got like 9 of them sitting at at let's say every this one pixel location. And all that you are saying is, when from this n by n volume, when you go and map it, right, it will map to some area in the image. Now if in that area, if there is a ground truth box,
If in that image,
if in the image, yeah, because I know the input image, right, I know that right, I have this image, and I know that I have a ground truth box here, I have a ground truth box here, I have a ground truth box, that I know, that information I know. So when I go back, right, if it maps here, then I know that there isn't anything of interest, because I know that right, a ground truth box is not there. But then suppose if at some stage, when I keep on sliding, right, what will happen, you will encounter this, you will encounter this, you will encounter this, right, because you are going to sweep the whole volume. That's why I said it's sliding. So at a time you can only do locally, that's why you can't go back fully.
yeah,
Okay, you have to do it locally. That's why I said that the sliding, see, I mean, right, people do not like, people frown upon any kind of sliding thing, because then it means that it takes time. But then in this case, right, I don't think, I mean, I don't think that anybody has said anything bad about the sliding idea. I mean, it's not even emphasized that much. Actually, if you have to do a careful reading of the paper, then you understand that it's a completely local operation, because you know, if you just take the whole thing, you know, then where is the locality? It will go to the whole image, right? It doesn't really help.
yes,
So it's sort of, because you see, finally region proposals have to come locally, right? During inference time, what do you have? You only an image, right? You don't have anything else. Therefore, it has to say from this region should something be shot out or not, right? I mean, you know, as interesting, right? I don't know, right? Some of you can still kind of, right, you know, think about something like an extension which wouldn't need a sliding window, but in this case, it's certainly a sliding window, okay? And then it goes over the volume, and then for every sliding window, you have these proposals that are coming out, that are already sitting there, and then if there is a ground truth box, it's finding the IOU with respect to each of these boxes, and somewhere you get an IOU which is reasonable. It could be more than one box, all that is fine. Those are all trained as 1 or 0.
that pixel, that particular anchor box will get flagged.
That anchor box, or maybe more than one, that pixel can also get flagged.
And finally, how do we generate this?
How do we?
How do you generate the final bounding box?
How do you generate? Yeah, so I said, no, you have a sibling layer here. So after this is exactly the same as the fast RCNN.
Okay.
You have a 4-dimensional bounding box regression, then you have a classification. This part is identical. Only what is coming in as a region proposal is coming from a network, instead of coming from some selective search module or something. And of course, the way the training is done, right, I mean, there are actually 2-3 ways of training this, but I think the most common thing is what is called alternating training, in the sense that, right, they train RPN. Actually, you know, I mean, right, details you have to kind of, right, go through the paper. That's why I said I'm not going to go through the details, but really the way they do is there is some sharing of convolutional layers and all, okay, between these two, between the fast RCNN which is sitting down, and then the RPN which is sitting up. So they train the RPN, come back, train the fast RCNN, go back, train the RPN, and then in between there is some sharing of convolutional layers, weights of convolutional layers and all. So it's a little complex, the training part. Okay, it's not like the first one is trained, done, and then you come to fast RC. They do what is called alternating training. Okay, so anchor boxes, yeah. So right, you asked, right. So I think, so if you think of anchor boxes, right, that's how they would kind of look like. And then right here are some faster RCNN outputs. Okay. Now finally, right, there is this, not finally, I mean, as far as object detection is concerned, right, there is this YOLO, right. What does YOLO stand for? You only look once, right. So you only look once. But then the idea is like this, right. So when you say that you only look once, right, what it means is that the YOLO network, right, as it is called, right, it kind of takes one look at the entire image. Okay, so that's why we call it as you only look once. So where is the region proposal and all? It's like, you know, you take a proposal from there, take a proposal. So the context information sometimes you may lose there, even though you can argue that, oh, you have an AlexNet, right, which is the backbone that has actually seen the entire image while training. Therefore, it must be having context and all. But that is all implicit. But then here it's actually it's straight away, it's also in a way implicit. But then here, right, you're not kind of looking at doing it that way, right. You just take an image, you take one look at it, and then say, right, what should be the right, where should I have these boxes. Now and it's very fast, right, by the way, right. I mean, you know, the other ones are also faster RCNN, I think, is also reasonably fast, but then this guy is like, you know, 45 frames per second, so it runs in real time, and there are various versions of this. Now the right, only thing, right, that I thought actually it's a simpler network, right. So the way this works is as follows. Okay, now So right, let me just give you a hang of how this works, the YOLO network, right. So what it does is, right, so the idea is like this, right. So it actually, so if you have an image, right, which you would like to, okay, for which, right, you would like to have these bounding boxes, right, around objects of interest, and what it does is, it actually splits this into an automatically, right, splits this into an S cross S grid. This S is a hyperparameter. Typically, it can go from 2 to 19, and 19 is very common. That means you really have like fine boxes there. So each is called a cell, a grid cell. Okay, so it's like this, right? So what it does is, see, for example, okay, let me just, okay, now what can happen is, okay, let me just build this up a little bit more. Okay, and then let's say we have some things here. Okay, so we have an S cross S grid, right? Now the way it works is that, for example, now what it will do is, see, I mean, if the center, I mean, suppose I have, a ground truth, this one, a bounding box, right, which is here. Okay, so for example, right, I mean, now the idea was that, I mean, I wanted to draw a box, right, which is not exactly centered in this grid. Okay, imagine that, let's say, right, that this box is centered there. Okay, even though that's not the exact center. Okay, so it's some box, right, which is sitting there. I have an object there. Now this grid cell, right, whose center, so this grid cell, as long as it contains the center of some sort of a ground truth box, I mean, so for the time being, right, we will actually assume that we have only one object, okay, per this one, right, a grid cell. A grid cell may contain a center, may not, but if it contains only one center. So what this means is that then we say that this grid cell is actually responsible for that object.
This is cross is grid cell.
No, this grid cell, wherein the center is falling. This ground truth box is there. No, I am saying that it has a center here, let's say, it's a little skewed, but let's say the center is there, but that's falling in some grid cell, right. Now that grid cell is supposed to be responsible for that object. Okay, so for example, okay, which means that this grid cell is not responsible. But then maybe some other object comes and sits, right, whose center is, let's say there. Okay, then this grid cell will become responsible for that object. Okay, so what it means is, if the center of the ground truth box sits in a grid cell, then that particular grid cell becomes responsible for that object.
Only that grid cell.
Only that, right, grid cell. Then what it does is, just like you had anchor boxes there, right. Now for each right grid cell, you can actually think about different shapes of bounding boxes. Let's say, right, the number of bounding boxes is B per cell. This is again a hyperparameter. Okay, you can choose it as phi or whatever, right. You can choose some hyperparameter. Now what it does is, so the way this works is, right, so the way to kind of understand this, right, this is actually, a Google net, okay, with some small things, right, with some small small things that they have changed here and there, right, more or less a Google net, but then it is this kind of a tensor that you have to see at the output. Now this output tensor, right, is what they want. So they want this network to actually produce a certain output tensor. Now until now, right, I said that, right, we will not actually worry about the size and all, I won't go to, but here I have to. Now the 7 cross 7 by actually a 30, right, where it actually comes from is because we want this network to actually predict this volume. What this volume actually means is that okay, is the following, right. So the 7 cross 7 is actually, let's say, for the case when S is 7, okay, and this actually and this 30, right, is coming because of the fact that I think for 30, right, so the way they have it is the number of classes, the bounding boxes are 2, okay, I think for this case, okay, for this particular case, I am saying you can choose bounding box whichever you want, and then there is another vector, right, which I will talk about. So every bounding box has actually 5 elements in it. See, right, think about this as some grid where as a grid where there are S square cells sitting, right, and in each cell, right, I have, let's say, a bounding box, let's say 5 bounding boxes, whatever, B number of bounding boxes, and for each bounding box, right, I will have certain elements which I want this network to output. Okay, that is what I want. This output tensor should be that. So what you want is a bounding box for which, right, it should tell a confidence score, which is given as one sort of a parameter S. This confidence score will mean that if you took that bounding box and if you did an IOU with the underlying ground truth box that is sitting there, then if you get a high value of IOU, that means your confidence is higher. That you can do now, because you know where the actual ground truth box is, and then you have these 5 boxes for that cell. So, you find out what is the kind of IOU that you get with the ground truth box. If S is high, it cannot be of course more than 1, right. So, whatever between 0 and 1, if it is high, then we know that okay, that is very likely this is a potentially good bounding box which could contain my object of interest S, and then it has an offset Bx and By, which will be the offset which will actually tell where is the ground truth box center relative to the where is the ground truth box center relative to the bounding box center. And if you take all bounding box centers to be about the center, then that offset will be the same for all of them. Then you will have Bw and then B height. What this means is how much should you scale your bounding box along the whatever, right, along the width and along the height in order to be able to match up to the ground truth box. You get this? Okay, so these 5 are for that bounding box. For each bounding box, you got like 5 things, right, which you want to find. One is a confidence score, second is an offset, and then third is the scale. Think of scale factors, offsets, and this one a confidence score. Then this 30 number is coming because in addition to this, right. So, when we generate a feature vector, right. So, when we generate this output, right, this is like, I mean, if you go along the depth, right, if you take, so it's like all your cells are sitting here, right, you have to see 7 cross 7, these are your cells, and for each one of them along the depth you have actually a 30 cross 1 vector. That vector is nothing but these 5 elements that I actually put here, that is S and then all the way up to whatever BH, this 5, okay, and yeah, this is for a cell, right, yeah. So, this 5 into, let us say, right, I mean in this case I have taken B to be 2, right, okay, that means you already have 5 parameters for one bounding box, correct, 5 parameters for one bounding box into 2 bounding boxes for which I have to find out, that is already 10, and then the number of classes, number of these classes, which is in this case actually 20. So, the actual feature, right, it is like this, you can think about this as S into B into 5 plus C. So, C is the number of classes. So, what this feature vector, right, we really will look like, right, is as follows. If you look at this vector, right, it will look like this. Okay, it will actually look like all these guys, right. I mean, see for example, I mean if you have 2 bounding boxes, then you will have say 10 elements there. If you have 3 bounding boxes, you will have into 3, right, 15. That is why this is 5. Okay, this is not S. This 5 is fixed. That is not a hyperparameter. That is fixed. That is confidence score, 4 other values. We got, yeah, confidence, offset, and scale. So that 5 is fixed. This is this is not fixed. This actually depends upon what kind of a database you have. So, C is the number of object classes in your data set. B is a hyperparameter, which is the number of bounding boxes, and S is the grids, number of grids that you have, that is decided by S. Huh?
Number of bounding boxes means the number of bounding boxes whose centers are lying in that particular
in that cell. In that cell, you could also shift the center if you wish. In which case you will have a Bx, By that will change for every bounding box. That is why I think they have left it. They left it free. Okay, now. So, which is why I am saying it is like B into 5, because you are assuming that everything could have an unknown. Okay, now, you have a B into 5 plus C, okay, C is the number of classes. So, here, right, so now what will happen is, right, so you have all these guys, right, which are related to the bounding boxes, then actually think about like classes C1 to let us say C20, and then this will be a one hot vector, which will say that, right. So, what this means is with respect to my ground truth, okay, see this is what I want as output. In my output, right, I will say that if I have a ground truth box there, I will know what should be the offset with respect to each of those boxes, what should be the scale with respect to each of those boxes, and then what should be the class, right, that should come out, right. So, that is like one of them will be a 1, everything else will be a 0, right, that is my kind of a feature, that is my output tensor, expected tensor, and you are trying to learn this, make this, and you are trying to train this network such that it outputs that tensor. That means for every bounding box, right, it should know that if I move by this offset, if I move by this scale, if I do this, then I will sit on top of that ground truth box. And again, right, you can have again multiple boxes coming, then you do an NMS exactly the same way, pick the guy which has the highest confidence score here, S, and then you do an intersection with the other boxes, wherever the intersection is greater than 0.5, throw them all out. Okay, that is how you do the NMS, exactly similar to, right, how it is done in RCNN. But then actually the overall network is actually pretty simple. This is all that is involved. This is all it is, right. You are just asking for an output tensor. and there you throw all of so you see, right, that right, you are not really talking about a region proposal network. This is one shot, right? Look at the whole image, produce that tensor. That is YOLO. That's why it's simple. I mean, it's simple once you understand, right, is how it is doing, right? Then it becomes simple. The only catch is that, right, for example, sometimes, right, you could have for example, right, a car here, and then you could also have, let's say, this bounding box is a car, and then you could have another person standing in front of that car. Now, right, I mean, if you look at the way, right, you are doing it, right, I mean, you are only allowing one class per cell. So now in this case, right, in that cell you have centers of both. Let's say the center of the person is also coming, because there is a ground truth box for that person. Then you have a ground truth box for that car, and let's say both of them are coming somewhere inside, right? They don't have to be the same place. One falls somewhere here, one falls, but both are falling into that grid. Now this original thing that we said will not allow that, because it will certainly say take one. But then that's not a good idea, right? You want to also say that there's a person sitting there, because this grid cell should be responsible for both. It cannot say that I am responsible. So what they do, what will you do? So they simply do a concatenation for this other one. What happened? I mean, in the sense that you had this one vector, right, this for one object class. No, you do a concatenation, wherein the other label will get flagged as one. I mean, if this was C5 car, then maybe C7 will be one here.
How many concatenations
that is up to you. That's what you have to decide, how many times such a thing can occur. I mean, if you underestimate it badly and train with 2, but if there are 4 guys coming together, then there could be a problem. Yeah, that is something that you have to think about. But that's all they do.
That one, that's also hyperbolic.
Yeah, see, one other way to avoid this kind of multiple thing is make S really large. That's why I said 19, right? So the chances that 2 centers will come in a box is little. So that's how you can take care of that. I mean, right? So you just make it really small, right? So that of course, even then it can happen. That's why they say, right, beyond 2 and all, probably it's not even needed. I mean, you don't get 4 guys coming into one grid cell. As long as, that's why I said 19 is the higher side, right? You don't take the lower one. You don't take 2. You go like 19. So you go like 19 cross 19. You divide the whole image into 19 cross 19 grids, and then you flag. Okay. Now that's about the detection, object detection. Right, so we saw RCNN, we saw faster RCNN, we saw faster RCNN, we saw YOLO.
What is the difference between the 2 bounding boxes and more than one object coming out of the same?
Yeah, 2 bounding boxes will have the same class label. Whereas if you have 2 objects, then your class labels will change. That's why I said then you'll have to actually attach, you'll have to do a concatenation. You have to concatenate to tell that there are actually 2 object centers sitting there, 2 different classes. Two possible boxes, out of which you may finally take only one after do non-maxima suppression and all. But when you have 2 object classes center sitting there, then it means that you want to flag both, right? You want to get a bounding box for this as well as that, and that you have to flag, because then you cannot have the same label for both. So the class label will have to change, right? That is the reason why you need actually one more concatenation, where you will say that there is another class label that should be 1. So it's not the same.